Okay, hello logic class, welcome back. In the previous video we proved this theorem which I called the bounded monotonic sequence convergence theorem. This is something you have even heard of. It's the thing that says if you have a sequence of real numbers which is bounded above and monotonically increasing, then it has a limit. And I was mumbling a little bit of various things like, what is this good for? And I looked into it. It even comes up in your calculus textbook a bunch of times. It's like the proof of the integral test, and in fact, it's the proof of the comparison test, the limit comparison test. Virtually all of the proofs of the various convergence theorems for series use this kind of theorem at a very low level. Well, what's another thing you can do? Oh, and I'll just say, for continuity with the previous video, that the theme of this is our kind of introduction to analysis. So the sort of the real name or the correct term for this kind of branch of calculus, or in America at least, when they say analysis, they mean kind of calculus done at this kind of very high level. And what did we do in this previous video? We showed how the least upper bound axiom for the real numbers can be used to prove this very low level theorem. Alright, well, what can you do with this very low level theorem besides some fancy things that you've already been exposed to? Well, another thing that you can do with this theorem is you can prove the Bozanovirustras Theorem. Alright, what is the Bozanovarstras Theorem? Well, it's an extremely important theorem. So important that, in the first sort of like 2 weeks or something of any serious analysis class that you take, you will prove this theorem, and then you will use this theorem sort of over and over and over again. This is a theorem kind of lies at the very heart of analysis, of calculus, and yet, for my audience of people, high school seniors taking this logic class, you have never heard of this theorem before. Okay, so that's a little bit alarming. You've never even heard of this theorem, which in fact is one of the most important theorems of calculus. Okay, what does the Bozanovirustras Theorem say? Oh, and by the way, Bosano, we will learn more about him later. He's this Czech mathematician who kind of labors in relative obscurity for his entire life, and almost all of his work is published after his death. And so turns out there's a huge number of things which became very important, which were first done by him, but maybe independently discovered by other people. So he wasn't that influential, but Weierstrass reproves this theorem towards the end, 1860s, something like that. Okay, what is this theorem, the Bozano-Weierstrass theorem, that's supposedly so important? Well, every bounded infinite sequence of real numbers has a convergent subsequence. Oh my gosh, where are the tangent lines? Where are the areas under the curves? Okay, I'll stop with all that. This is calculus, I guess. We're talking about convergence, so some kind of calculus is going on. What do we have here? We have a sequence of real numbers. Okay, so I had some sequence of real numbers. Great. The sequence is bounded. There is a convergent subsequence. Alright, so what does that even mean? It's possible you've never heard of this notation before. In fact, it's likely. This term, subsequence. What is a subsequence? So take some sequence, x1, x2, x3, x4, etc. So that's a sequence. Maybe I can take that out. Maybe throw in some more here. x5, x6, etc. So, it's a sequence, so it comes in a particular order. What is a sequence? Is sort of a function from natural numbers to real numbers. So it puts a set of real numbers in some kind of order like this. Okay, well, a subsequence is just a new sequence that you sort of construct out of an old sequence by selecting just some of the terms. And this will come up later, so maybe if we call this arbitrary sequence, if we call it sort of an arbitrary term in the sequence x of n, we may select, just like this one, etc. So then, you know, x2, x3, x5 is a subsequence. So a subsequence is just a new sequence constructed out of an old sequence in which you take some of the terms of the sequence, but you keep them in the same order. Okay. And you even might call this x sub n sub k or something like that, because though this is I want to be able to sort of doubly refer to this term as the fifth term of the original sequence, but it's like the third term of the subsequence, something like that. Okay. Well, great. So what is this now saying? What this is saying, you have some kind of sequence, and I kind of want to maybe plot it, because what do I know about the sequence? Well, almost nothing. I just know that it's bounded, that's it. So if my sequence is bounded, then all I can say about this sequence, this is extremely general, is that there's some kind of upper bound, so call it m. And the sequence never goes above m. But otherwise, man, this sequence could do anything. So if I were to sort of plot the terms of the sequence and try to make a picture, I mean, there's just almost no, kind of thing whatsoever. All right, I have way more dots than I have tick marks along my horizontal axis. But anyway, there's my sequence. It could be anything, but it's just bounded. That's it. And somehow, yet, despite this, seeming kind of randomness or something like that, I may extract from this sequence some subsequence of terms which in fact have a limit. And yeah, that's really saying something. And of course, to have a limit, so we have sort of an infinite. I guess that's kind of implied, right? That this subsequence is in fact infinite. So I can sort of find an infinite number of terms of this sequence by ignoring some terms of the sequence. I can construct, by focusing, so to speak, on only some of the terms. I can make a sequence which has a limit. Okay. All right. How can we do this? Well, we can do this by defining something called a peak. So what's a peak? A peak of a sequence. A peak, and I guess it doesn't matter. Yep. Okay. So here I'll just stick to my notes exactly. So let n be a peak for this particular sequence if x sub n is greater than x sub m for all m greater than n. For all m greater than n. Okay, so what's a peak? A peak is like, it will never be this good again. You are at a peak. If peak doesn't mean best, peak means, maybe I'll even just write this, right? So sort of at a peak, it will never be this good again. All right, and so it's not the best day of your life. It's not the maximum of the sequence. It's just the best day of the rest of your life. You're a peak if things are pretty good right now, and in fact they're as good as they're ever going to be again, because things are better now than they are going to be for every subsequent term in the sequence. Okay, so there are only 3 possibilities with respect to peaks. I mentioned that besides being bounded, there seem to be almost no there are no other kind of requirements whatsoever put on the terms of this infinite sequence. But okay, by introducing this concept of peak, I can now say that there are 3 possibilities. So here are the 3 possibilities. You could even argue that really there are only 2 possibilities, but that's what I'm going to do. Either there are an infinite number of peaks, there are a finite number of peaks, or there are no peaks. Okay, let's check it out. So infinite number of peaks. That's one option. Finite number of peaks, and just no peaks at all. Okay, and let's just make a picture associated with each of these possibilities. What does it mean if there are sort of an infinite number of peaks? Well, it means that it means that you have a peak. All right. What does it mean to be a peak? It means that things are never going to be this good again. This is the best day of the rest of your life. And perhaps it took some while to get there. Okay, but if there are an infinite number of peaks, it means that later on there's going to be a new best day of the rest of your life. Well, the best day of the rest of your life. So once a certain point once this is designated a peak, it means that every subsequent term of the sequence will be less than this value. Okay, so this is the best day of the rest of your life. So now things are going to be lower and whatever, but then there's another peak. Okay, so what is this kind of next peak? Well, this is, again, the best day of the rest of your life. It's not as good as the previous peak, but it's still the best day of the rest of your life. And since it's the best day of the rest of your life, no subsequent term can ever go higher than that. So things are going to do, whatever they're going to do, going up and down, maybe very far down, maybe up, but never that high. Okay, and then there's going to be another peak. Okay, and so if there are an infinite number of peaks, then though the behavior though this sequence might be extremely chaotic, by only focusing my attention on the peaks, things are in fact just getting worse. Okay, you should sort of feel that. This is like some, one year I described this as some kind of like weird, bad indie movie like 500 Days of Summer or something like that, right? Where you write a journal entry and you rate every single day of your entire life in some kind of objective scale, and then you plot every single day of your life as some kind of sequence. And this is one way that your life might go, right? Everything is amazing, and little do you know it's never going to be that good again. And then later on, there's another day that you perhaps don't appreciate, where, man, it's never going to be this good, it's never, and then it turns out only in retrospect that, things never got this good ever again, etc., etc. Well, one may then extract, hopefully you see where this is going, one may then extract just the peaks. So I'll just, instead of writing this down, I'll just say this out loud. What am I trying to do again? I'm trying to find a subsequence which converges. Well, does this, oh, by the way, bounded was in the top and bottom direction. I forgot to mention that. So let me just throw in another thing down here. Call it big N. Bounded meant, I just realized right now that bounded it was implied that bounded above and bounded below. And so, anyway, that's relevant right now because I say that the subsequence of peaks is the subsequence to look at. So if I now just select all the peaks, and remember I'm in the case in which there are an infinite number of peaks, then what can I say about this subsequence of peaks? Well, by the definition of peak, each peak is lower than the next one. And therefore, this subsequence of peaks has the following property. Well, it's monotonically decreasing. Is monotonically decreasing. And here's what I know based on the previous video. Here I have a sequence. It's bounded. In this case, what's relevant is that it's bounded below. And if you have a sequence which is bounded and monotonically increasing, or in this case it's monotonically decreasing, then it can't decrease forever because there's a lower bound. And so if it can't decrease forever, but it can't ever go below big N, I should say. So it's monotonically decreasing, but bounded below. Therefore, this subsequence has a limit. Subsequence has a limit. In other words, I apply the theorem from the previous video. I apply the theorem that says that any monotonic sequence which is bounded converges. That it has a limit, right? So that's any monotonic sequence of real numbers that is bounded has a limit. Okay, so here we use the bounded below version. Okay, hopefully that's clear. In other words, okay, even just to be even more explicit about it, there must be some limit L to which these peaks are terrible line. There must exist some real number L to which this subsequence of peaks is approaching. And in fact, we saw in the previous video that L is actually just the least. In this case, it would be the greatest lower bound of the set of peaks. Okay, what's another option? Another option is that there are a finite number of peaks. In other words, stuff happens, then there's a day that's the best day of the rest of your life. Then stuff happens, there's another day that's the best day. Perhaps there's like, 2 or 200 of them, who knows. But then, beyond that's like the last peak. Okay, so here we have a peak, and here we have a peak, and then at some point we get something which is the last peak. Okay, and once we hit the last peak, then afterwards there are no more peaks. And if there are no more peaks, then in fact, what does it look like? Well, it looks like the situation in which there are just no peaks at all. Okay, what does it mean if there are no peaks? If there are no peaks, then this is a kind of a very interesting life you lead if you have a life in which there are no peaks. It means that there's no day ever in your life in which that day is the best day of the rest of your life. And if you work out the low-level logic behind that, then what that means is that things are just getting better and better. Not necessarily every day things are getting better and better, but things might be quite terrible for many, many days in a row. But if you wait long enough, you will eventually have a new day, which is actually the best day of your life so far. That's what it means. That's what it really means if there are no peaks. Things might be good, and even though we got quite high up here, that's not a peak. And if I can point to a particular number and say that that's not a peak, what that really means is that later on we shall surpass that point. Which means that things are, good, bad, who knows, but eventually things are going to get better again. Better than the previous best. And things might do whatever they do, and then things are going to get better again, and better again, and better again. And so if you're living a life in which there are no peaks, it means that wait long enough, and you'll have a day in your life which is better than any day you've had in your life so far. Okay, well, I think you see what I mean now when I say that there are really only two cases, because as I'm looking as these sequences are all infinite, if I have once I hit the last peak, well then just kind of like start your analysis here, right? Because once we have so this was a peak, so that must mean that things never are this good ever again, but subsequently to that, there are no more peaks, which means what? Well, I guess that's kind of hard to say what it means. But it means things keep getting better and better and better and better. That no matter how long I wait, things are just going to get better and better and better. But you'll still never do as good as you did on that last peak. But things are still going to keep getting better and better. Okay, and here too, maybe this is a little bit misleading. This rise that's going on, seemingly forever, because in fact, recall that this thing is bounded. So since this thing is bounded above by M, then, though there will always be these days of your life that are the best day you've had so far, it's not like things are getting better and better forever. Well, they're getting better and better forever, but how good your life can be is bounded above by M. Okay, I think hopefully that you get it here. You let these new points, you construct your subsequence for these two cases, which is really just one case, out of the subsequence of days which are the new best day of your life up to that point. In other words, if you want to add a little bit more rigor to this, let's just go to the no peak case, right? Let there be, start with like some day, right? Call this x1. Okay, what should I set x2 to be? Well, let x2 be the next number which is bigger than x1. And there must be a number that is bigger than x1 because x1 is not a peak. So the very definition of what it means for x1 to not be a peak is that there must be some subsequent day which is better than it. So call that x2. Well, x2 is not a peak either because there are no peaks. So keep going out into the sequence far enough until you hit an x3 such that x3 is bigger than x2. And there must be such a day, otherwise x2 would be a peak, and it isn't because there are no peaks. And so you construct your subsequence out of the new sort of best days so far. Okay, and well now, and it's the exact same thing over here, except now this sequence of, well, this is the best new day of your life so far. These days are not the whole, I've never gone into this much detail before. These days are not the best day of your life so far. They're the best day of your life since the last peak. That's really what it was, right? So this is like maybe, this was a very traumatic day where things were amazingly great. And then they just never get that good ever again. Things are bad after that. But they still do keep getting better and better. That's something like that. All right, the analogy has been stretched way too far. But okay, what's the point? What can I say about this sequence? Well, this sequence is monotonically increasing. Monotonically increasing. This subsequence, this red circled subsequence is monotonically increasing. And once again, I've found a subsequence with a limit. Because by the previous theorem, every bounded monotonically increasing sequence has a limit. And so now I can't really tell what the limit is. It must be this kind of number, like this, something like that, such that these just keep getting bigger and bigger. And here, there's also some kind of limit somewhere down over here less than m. But once again, I have by applying this previous theorem, there is a monotonically increasing sequence of real numbers, so it must have a limit. It's the least upper bound of the set of these circled numbers. Okay, and so in all three cases, I can find a subsequence which has a limit. All right, that was like a very slow and trappy kind of explanation of this, but I think it's pretty good. If you take an analysis class in college, you'll do this same thing, but it will be a sort of a drier, more efficient presentation of this, and hopefully you will understand it better, although I think this is a nice presentation. Okay, now, I made a big deal. You feel free to stop this video now and don't continue watching, because that was all I kind of wanted to do. What you might be thinking right now is, dude, why should I care about this at all? What is the point of I cannot imagine the Bozanovaristras Theorem being useful in some kind of way. Alright, well here we go, and now I'm going to give a lesson on video that I have never given before, that I only learned an hour ago, that I've never taught, that I didn't even write it out in my own style. So this probably will be a low quality presentation of this topic. But hopefully I'll hand wave, when I get stuck, and actually I'm just going to give a little bit of it. Okay, and one of the things is, you can use this to prove is the extreme value theorem. Alright, what even is the extreme value theorem? It is so boring and simple and basic that you've probably even just forgotten about it. Or perhaps you remember. What's the extreme value theorem? It's this thing that says, if f is continuous on the closed interval AB, then f has a max and a min. Then f has a max and a min on this interval AB. Okay, so the picture is something like this. When I taught you analysis 1A, probably I explained it like so. Here I have a function. It's continuous, which means, no holes, no jumps, no crazy infinite behavior, nothing weird like that. And on a closed interval, well, there's a just very limited amount of kind of behavior that we can expect for a function if it's continuous. And so, okay, I have no idea what this function is going to look like, but I probably drew something like this. And yeah, this function must have a maximum and a minimum. That maximum could be a relative maximum. Usually people call this big M, and perhaps the minimum of this function, the minimum value, is the value at an endpoint. Who knows? Okay, so if you remember the sort of logical structure of calculus, the extreme value theorem gets kind of mentioned. In fact, okay, the average teacher probably spends 5 minutes on this because we definitely did not prove it. I mentioned it and everyone was kind of like, okay, sure, whatever. And then I sort of pretended that this was now a theorem that was very important, that you were supposed to kind of care about and know about, and it came up, very, very few times later on in the rest of this class. The one really sort of famous time that it comes up is that you use it to prove Rolle's theorem. Because what is Rolle's theorem? It's the one that says, if the y value is the same, then the derivative has to be 0 somewhere if the function is differentiable. And yeah, and what we basically said was, look, first off, if this function is differentiable, it has to be continuous. If it's continuous, there must be a maximum. And then we said, if there is a maximum, what did we do? We said, there must be a maximum because if the function is the same value at the left and right endpoints, then first let's take the case where the function is to be found somewhere above that y value. Well, if the function is above that y value, then there has to be a maximum, but the maximum can't be those y values, so it's got to be some relative maximum, and then we applied some fact about relative maxima, that their derivative is 0. Okay, so, oh my gosh, so we used the extreme value, I probably spaced this out sort of badly. We used this extreme value theorem to prove Rolle's theorem, and we used Rolle's theorem 10 minutes later to prove the mean value theorem, which is supposedly like super important, like, when proving the fundamental theorem of calculus, we use the mean value theorem. In fact, the mean value theorem gets used kind of all the time. This is another sort of creation of the 19th century, the mean value theorem. So okay, so everything was kind of resting on the mean value theorem, which is really kind of a special case or an extension. I guess it's an extension is the best way to put it, of Rolle's theorem. Rolle's theorem gets proved with the extreme value theorem, but in analysis 1A, and in fact in all classes, calculus classes all across America and the world, people are like, yeah, we don't prove that. We don't prove that extreme value theorem. And of course we don't prove it because it's one of these extremely low-level theorems, and the more low-level and sort of obvious your theorem, just like proposition 2 of Euclid, you are going to have more trouble proving it, sort of more obvious it is. Well, yeah, you can prove the extreme value theorem. An important lemma in proving the extreme value theorem is the boundedness theorem. Boundedness theorem. And what is the boundedness theorem? The boundedness theorem says simply that if a function is continuous on an interval, then it is bounded. So, boundedness theorem. Let's just prove one case, the bounded above case. So, so here we go. If f is continuous on the interval AB, then f is bounded above. Bounded above. Okay, that doesn't prove that it has a maximum. It just proves that it is bounded above. And once you know that it's bounded above, however, you can apply the least upper bound axiom. Because what you can do is, maybe I should put this kind of down at the bottom. I'm not even going to write it down. I'm just going to say it out loud. Once you have the boundedness theorem, I'm explaining now how to get from the boundedness theorem to the extreme value theorem. Well, once you know that your function is bounded above, then you create the set of all of the y values that that function outputs on that entire closed interval AB. And now you have all these y values. Well, by the boundedness theorem, that set is bounded above. And since that set is bounded above, I can apply the least upper bound axiom to that set. And the least upper bound axiom says that for any non-empty bounded set of real numbers, there is a least upper bound. And then the least upper bound of that set is some number, some y value, and then you go on to prove that in fact there must be some point on that interval, which when you plug it in gives you that least upper bound. So you sort of construct the maximum. The proof of the extreme value theorem is that you construct the maximum by knowing that that maximum is in fact the least upper bound of the set of all the y values, and then proving that that maximum is obtained via some convoluted process. Okay, so what the hell is the boundedness theorem? The boundedness theorem, for the boundedness theorem, we're just proving that the function is bounded. So all I now want to say is that given some function on some closed interval, that, it's not unbounded, you might say. So there must be some big M. Now, big M is not the maximum of the function, it's just some upper bound. Okay, think of this as a lemma so that one may apply the least upper bound axiom. All right, I've said that now 4 times. Okay, how am I going to prove the boundedness theorem? Well, I'm going to use the Bolzano Weierstrass theorem, of course, that I just proved. And the Bozanovarstras Theorem comes from the bounded monotonic sequence convergence theorem, which comes from the least upper bound axiom. Alright, so if you're getting a feel for all this, man, I used the least upper bound axiom to prove the bounded monotonic sequence convergence theorem, which proves the Bozanovirustras Theorem. We've seen all that already. Now I'm going to do this one right here. I'm going to kind of half do it. And I sort of sketched how you would do that. And so, okay, the whole sort of world of calculus is now kind of coming into focus a little bit. How do I do this? Okay, I really barely understand this. I'm not being humble. Okay, here's what we do. We say, okay, well, suppose not. So suppose not. And so this whole thing is going to be some giant proof by contradiction. Okay, so what does it mean to not be bounded above? Well, if you're not bounded above, then it must mean that that there's no number which is greater than every one of the outputs of this function, which is another way of saying, or which can be sort of rephrased at a low logical level as, for any y value that you ask me for, I can always find an output of the function which goes beyond that. Okay, so now what I would like you to do is to sort of consider a sequence of challenges. A challenge 1, a challenge 2, a challenge 3, a challenge 4, and sort of never stop, right? What are these numbers? These are numbers that you are demanding that your function surpass. And it will, because the function is unbounded by this assumption, which is going to lead to contradiction. Okay, so maybe like, maybe I'll do something like this, right? Like take take b equals 1. What's b? B is sort of b is kind of an upper bound or something like that. It's a proposed upper bound. But on the assumption that this function is not bounded above, then based on the definition of what it means to be not bounded above, there must be some x value. X1. What is x1? X1 is on the closed interval AB, and what can I say about that x1? Maybe I should write such that f of x1 is greater than 1. Okay, and now you take a new challenge. Set b to be 2. And now, so now you're saying, I bet you can't find a y value of your function which is greater than 2. Oh, I can, because I have made the assumption that this function is not bounded above. And if it's not bounded above, then given challenge 2, I can certainly find by assumption, an x value somewhere on this interval AB such that f of x2 is greater than 2. And similarly, we just keep doing this, right? For a challenge of 3, I can always find an x3 that's an input such that f of x3 is greater than 3. Okay, and I'll just write like ... What have we just constructed? We have just constructed a sequence. So we have this sequence, and what is this sequence? It's the sequence x1, x2, x3, etc., and xn, whatever, and it's a sequence of x values drawn from the interval AB, which the sort of defining property of it. So I'll just write sort of such that f of xn is greater than n. And it's possible to construct such a sequence because we've made this poisoned assumption that this function is not bounded above. Okay, well, what do I do with this sequence? I now apply the Bozanovaristras Theorem. I'm looking at my phone because I have a screenshot from Wikipedia. Am I doing this right? I am. Yeah. Geez. Okay. So now we apply the Bolzano-Weierstrass Theorem that I said was so important to this sequence x of n. Okay, hold on. Is the Bozano-Weierstrass theorem applicable? What are the requirements for the Bozano-Weierstrass theorem? Well, you need to have a sequence which is bounded above and bounded below, and yeah, I guess that's just it, right? And it has bounded above, bounded below, and infinite. Well, this sequence is bounded above and bounded below because this sequence is just a bunch of x values, all of which are drawn from the closed interval AB. And so, in fact, this sequence is bounded below by A and bounded above by B. Another way of putting this is, though we might have some kind of insane sort of chaotic behavior, what should we perhaps make a picture of these x1s and x2s and stuff like that? Maybe that is a good idea. Because that's 1, that's 2, that's 3, that's 4, etc. And I have no idea sort of what this function is doing. I'm trying to do this extremely generally. But what I can say is, by assumption, there is always some point x1 which is bigger than 1. And there is always some point x2 which is bigger than 2. And there's always some point x3, so these numbers are not in any kind of order, right? These are just the sort of responses to the challenges, and so this is kind of a crazy sequence. This sequence is itself not monotonic. Do not get the impression that x1, x2, x3 are sort of in order. That those real numbers are sort of getting bigger. No, they're not. They're the numbers on the interval AB, which, when you plug them into the function, give outputs which are which meet the demand of being higher than the natural number challenge. Okay, so it's getting so complicated. So this is 1, that point's higher than 1. This was 2, that point's higher than 2. This was 3, that point's higher than 3. This is 4, that point is higher than 4. So maybe draw some little thingies in here or something. Okay, and so there's this kind of chaotic sequence. I think of this sequence as being kind of chaotic, potentially chaotic. But the Bozanovaristras theorem says it's okay because don't look at the entire sequence, just focus on some of the terms of this sequence. And the Bozanovaristras theorem applied to this sequence produces a new sequence which in fact has a limit. So we have a new sequence. And okay, this is a crazy thing to do, but we're going to call this, x sub n sub k, which has a limit. Okay. In other words, we had this sequence x1, x2. x3, x4, x5, x6, x7, etc. But the Bozanovarstras theorem says that there's some subsequence. So maybe just x. You take x2, x3, x5, etc. And then this I will hereby name like x sub 2 sub 1. This I will name x sub 3 sub 2. This I will name x sub 5 sub 3. So it's a subsequence. And what's true about this subsequence? It has a limit. Okay. It converges to some sort of value. Okay. So let's let the limit as and now sort of this new sort of index now is k, right? K is now the letter which tells you sort of what term of the subsequence you're on. So we'll just let the limit as k goes to infinity of x sub n sub k. I can't believe I'm writing this, but that's what people do. Let this be some number. Let's call it c. And let's not forget that c is an x value, so to speak, right? C is a number that these numbers are converging to. And what are these numbers? These are just numbers taken from the interval AB. Okay, so what is c? C is going to be just some point on the interval AB. That's just a fact about this number c. It's a real number. It's the limit of this sequence. And what is this sequence again? It's the convergent subsequence of this other infinite sequence that we constructed. Okay, where is this going? Well then, yeah, boom. And I suppose there's some sort of work to do to show maybe, or maybe there's no work to do, to show that this limit has to be, so C is itself, I just said this, but perhaps you need to argue that this limit is a real number on the interval AB. That doesn't sound like that would be too hard. Okay, blah, 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 blah. Okay, now you say, okay, but f is continuous. Here I use the continuity of f. And that by the continuity of f in some way that I don't really want to get into, I will now consider a new sequence. And this new sequence I'm going to consider is f of x2, 1, f of x3, 2, f of x5, 3, etc. In other words, let's make a new sequence which is the outputs of all of the elements of this new subsequence that we got from the Bozanovirustras theorem. And, well, what can I say about this sequence? I hope you agree that by using some facts about continuity, okay, well, what does it sort of mean to be, there's some more level of detail that I could go into here if I had maybe like a larger board or more patience, but, right, because it's continuous, you know, what does it even sort of mean to be continuous? That you know, no matter, okay, let me just state what I'm trying to say first. The sort of conclusion is that this sequence has a limit, and that limit is going to be f of c. It's extremely plausible that if you have some sequence of inputs which converges to c, and you construct the sequence of outputs, then if these x values are getting closer and closer to c, then of course the y values need to be getting closer and closer to some kind of number, because, well, they just must, right? Because for some sort of epsilon, I have to get sort of, let's see, that's just based on the definition of continuity. There's some sort of other definition of continuity happening here. Okay, I'll stop talking if I can't say anything good about that, but I think that's what you do. Okay, well, now what? Where is this contradiction supposed to be coming from? Well, here we go. Here's the problem. The problem is, on the one hand, you can show that this sequence is going to f. But on the other hand, so you have that the limit as k goes to infinity of x sub n sub k is in fact f of c. Okay, but also let's not forget that these x values had a very certain property. So what can I say about f sub x sub n sub k? Well, first of all, it has to be based on the construction of the sequence. This is f of x sub n sub k I'll just say it, is going to be bigger than n. But that's just not possible. Because on the one hand, you have these y values approaching some very particular number f of c, but on the other hand, the farther out you go in this sequence, the terms are that basically the very construction of the original sequence x1, x2, x3 was such that the y values are supposed to keep growing and growing forever. So maybe I'll sort of leave it at that, right? On the one hand, the y values are keep growing and growing forever, and so the farther out you go in the original sequence, the bigger the y values get. So in the subsequence as well, the farther out you go, the bigger and bigger the y values get. And yet, on the other hand, we've showed by properties of continuity that these y values get closer and closer to this number f of c. And they must, because because the x values in this subsequence get closer and closer to c. Okay, and so sort of there's our contradiction. Okay, and so it's somehow, if I can now take a step back and try to sort of explain what's going on here, somehow, at some very basic level, this function can't be unbounded. Because if we're unbounded, you could go out, there would always be inputs to the function which made the y values just bigger and bigger and bigger forever. But if you have a sequence of x values which is itself bounded, the inputs are bounded. If the inputs are bounded, I can't have a bunch of bounded inputs which produce unbounded outputs if the function is continuous. Because though there may be some sort of no matter what kind of chaotic behavior might be going on among the inputs, the Bozanovaristras Theorem says that though there might be some chaotic sequence, if that sequence is bounded and the x values, our inputs come from this bounded interval, then there's some pattern, not pattern, there's some structure, there's some subsequence which has a limit. And so one can find some sort of subsequence which does approach some particular x value. And now, because the function is continuous, I do really get this. Because the function is continuous, if the inputs are getting closer and closer and closer to some number c, cha, then by properties of continuity, then the outputs are getting closer and closer to some y value f of c. Contrary to the fact that the farther out you go in the sequence, the y values keep growing and growing. Okay. Good. What does the Bozanovirustras theorem sort of do? It enables you to kind of tame a sequence in some kind of a way, to kind of find in and amongst the chaos. The Bozanovarstras theorem enables you to sort of find some part of it that's doing something that's kind of coherent. I guess that's kind of what's going on here. All right, woo! That was a proof of the Boundedness Theorem, something I only learned an hour ago. Once again, it's the least upper bound axiom, which is lying sort of at the heart of all of this, which gets used kind of again and again, by the way, multiple times. I think I said that it's going to play a big role here in the construction of in the proof of the extreme value theorem from the Boundedness Theorem, which I'm definitely not going to do. But we showed how it can prove, and this is the end of this kind of thing. We showed how it can prove the bounded monotonic sequence convergence theorem, how that can be used to prove the Bozanovarstras theorem. Now we've seen how the Bozanovarstras theorem can prove the boundedness theorem. I sketched a proof kind of that of the extreme value theorem from the boundedness theorem by simply applying the least upper bound of all the y values. Now that I know it's bounded, and this gets used in the proof of Rolle's theorem, which gets used in the mean value theorem. So okay, whew, goodbye.